Now, since displacement is little x minus big X, then the displacement gradients del ui del big XR equal del xi del big XR minus del big xi del big XR, which is FIR minus delta IR. In other words, the displacement gradients, which are grad of u, and the capital G there is intentional to represent derivatives with respect to the reference coordinates, which we call G, is equal to F minus I. So G is the displacement gradient tensor. It's just the deformation gradient tensor minus the identity tensor. But it's the deformation gradient tensor that we'll use most, and that's thanks to the polar decomposition theorem. And the polar decomposition theorem states that for a matrix or tensor, such as F, that is square and non-singular, it can always be decomposed into the product of R, an orthogonal rotation, and U, a symmetric tensor, or alternatively, the product of the symmetric tensor V times R, the orthogonal rotation. So here, R is the orthogonal rotation tensor. It has the property that R transpose R equals I, or R transpose equal I. And U is the symmetric right stretch tensor. So U is equal to U transpose. In the alternative form of the polar decomposition theorem, V, which is also symmetric, is called the left stretch tensor. So V equals V transpose. So the deformation gradient can always be decomposed into a stretch and a rotation, because that's the two things that can happen to the vector. It can change its length and it can change its orientation. Now, since the rotation could be a rigid body motion that could be indistinguishable from a change of observer, we really want to get rid of R. We're really interested in shape change, and shape change amounts to length change. So we want to find a tensor measure that preserves the stretch U, or V, but eliminates R. Now, U and V could be used, but the polar decomposition theorem is difficult to compute. So instead what we do is we square F and make use of the orthogonality of the rotation to eliminate it in the product. So we define the right Cauchy-Green deformation tensor, which is conventionally called C, by C equals F transpose F. F transpose would be RU all transpose times RU. And recall that the transpose of a product is the product of the transposes, but in the opposite order. So that gives us U transpose R transpose RU. But R transpose R is I, the identity tensor, which leaves us U transpose U. And since U is symmetric, that would be the same as U squared for short. In component notation, the components of C would be given by FIR, FIS, which would leave CRS, or del XI, del XR, del XI, del XS. And notice that if we switch the orders of R and S, we get the same expression. So C is symmetric, which we would expect because U is symmetric. And furthermore, notice that the indices of C are the capital letter, referring to the components of the reference or undeformed coordinates. So C, the right Cauchy-Green deformation tensor, is a Lagrangian quantity.